Hey guys, I just wanted to take a couple of minutes to summarize the answers to video number 1. So the first question, these are from your crash course video questions. So the first question asks, what are the basic characteristics of magnets? So here they are. Magnets have north and south poles, and opposite poles attract while like poles repel. Magnets are usually composed of iron or an iron alloy. In other words, they're mostly made of iron, but sometimes have other stuff like neodymium, for example. Nickel, cobalt, and iron are attracted to magnets. Magnets are surrounded by magnetic fields, with the magnetic field lines pointing from north to south. In other words, if you look at a magnet, a bar magnet, what you'll find is that arrows point out of the North Pole and they point into the South Pole. And these arrows will make loops. The more of these arrows you have, the stronger the magnetic field. It's just a little convention, I guess you would call it. Okay, so 2, what happens if you cut a bar magnet in half? You will get 2 magnets, and each of those will have a north and a south pole. In other words, you cannot separate the poles. Single polar magnets don't exist. And as I said previously, magnetic field lines form closed loops. Okay, the units used to measure the magnitude of a magnetic field are the Tesla, and they are named after this handsome chap, Nikola Tesla. Quite a smart guy, also one of the archetypes for the mad scientist. Later on in life, he went a little bit cuckoo. Interesting biography. You should check out his Wikipedia page. Okay, 4. What fundamental principle of magnetism did Ørsted discover? He discovered that a current moving through a conductor has a magnetic field around it. I almost wrote the word create here, and you want to avoid create in physics. We do not generally create stuff. We measure stuff that exists. There is my alarm. Okay, so 5, explain how to use the first right-hand rule and what it tells us. So if you grasp a wire with your thumb pointed in the direction of current, like this, then your fingers are going to be pointed around the wire, and those will indicate the direction of the magnetic field line. So generally we would call it clockwise or counterclockwise, but it depends on which way you're facing, right? So there you go. I've attached this diagram. This is from my IB physics book, by the way, to give credit where credit is due. All right, so what is the relationship between the force of a magnetic field and the current? Very straightforward. More current gives a stronger magnetic field. Okay, now we have another right-hand rule, and what it tells us is the direction of force on a conductor carrying current through a magnetic field. So we have these 3 properties. We have force, we have current, we have a magnetic field. Okay, so when we look at this diagram here, what you will see is that we have mapped each of those properties onto our 3 fingers, our middle finger, our index finger, and our thumb. So if you know the direction of any 2 of these elements, you can find the 3rd direction. And importantly, each finger should be at 90 degrees to the other. Okay, so you will find physics students during exams making funny hand gestures and then rotating them. Okay, that's part of the deal. So you should try this right now if you've not. So orient your fingers this way. Make sure that they're all 90 degrees to each other. So there'd be a 90-degree angle here and a 90-degree angle here, etc., etc. Okay, so what factors does the magnitude of force from a magnetic field depend on? Not an electric field, that was a typo. Don't confuse the two, it's easy to do that. Okay, so I have just written down this equation where force is equal to current times the length of the conductor times the strength of the magnetic field times sine of theta. So theta here is the angle between the conductor and the field. Okay, so you can imagine our magnetic field looking something like this. Okay, so here we have some magnetic field lines. And if we run a conductor through here, what we will find is that the strongest force will be obtained when the conductor is perpendicular to the field. Okay, so if we change the angle like this, then what's going to happen is, so let's add direction of current. This is a wire, and this is B. This is a wire, and this is B, magnetic field. Okay, so here we have an angle which we will call theta, and as that angle decreases, gets closer to zero, the force on the wire is going to decrease. And how much it decreases is dependent on sine of theta. Okay, so that behaves as a coefficient. Okay, so when will a magnetic field have no effect on a current? That is when the conductor is parallel to the electric field, and that angle, theta, is 0, okay? So sine of 0 degrees is 0, as you can see here, and that means that our force will be 0 by definition. Okay, what factors does the magnitude of force on a single charge from a magnetic field depend on? So if you imagine throwing a particle into a magnetic field, I don't know how you would throw it, but maybe just toss it, maybe have a particle accelerator. There are a number of ways to go about it. So in any case, here force is equal to the charge of the particle, Q, times the velocity of the particle, V, times the strength of the magnetic field. And sine of theta will be the angle between the path of the particle and the magnetic field. Okay, so in this case, you would have something like this, where you can imagine an electron or an alpha particle, basically a helium nucleus, positively charged. Those are a couple of examples. You can imagine this particle being shot with a certain velocity, and this is our velocity vector arrow, into the field, okay? And a force will act on it when you do that. Okay, so the third right-hand rule tells us the direction of force on a particle in a magnetic field, and the question does not ask to explain it, so I've not included a diagram here. If you have any questions, let me know. A lot of dealing with right-hand rules is just doing practice problems and then checking the answers. It's really straightforward, and it's pretty annoying, I'm not gonna lie. Okay. Second video, what would cause parallel wires to attract or repel each other? Just current flowing through the wires. So the basic logic behind Ampere's law is that the larger the current is, the larger the magnetic field produced will be. Okay, according to Ampere's law, what does the strength of the magnetic field at a given distance from the current depend on? We've touched on this in the previous question, and here we're going to kind of quantify it a little bit. In the book, they give you an equation that you don't really need to know. So I'm just going to say here that the magnetic field is proportionate to current, okay? So magnetic field strength at a given distance is proportionate to current. It's also inversely proportionate to radius. So we just add that down here. So in other words, the further away you get, the smaller the current will be. So the larger, or not the current, the smaller the magnetic field around the conductor will be. Okay, so that's about all you need to know mathematically here. Okay, number 4, what does a magnetic field inside a solenoid depend on? Again, current. More current, larger magnetic field. Why does a loop of wire turn inside a solenoid? So, a loop of wire in a solenoid has current running perpendicular to a field, but in opposite directions. Okay, so what that means is that the force on the loop is going to be in opposite directions. Okay, so you can imagine a loop, looks like this, loop of wire, and we put this loop into a magnetic field, and there's current running around the loop, and this current will cause a force to act on it. Okay, so the force in this case will point up. The force on the other side, where the current is moving the opposite direction, will point down, and that is going to cause the loop to rotate. Okay, so how does this explain how motors work? So a loop carrying a current is placed into a magnetic field, and forces act perpendicular to the face of the loop, and they turn it until it's parallel to the field. Now at this point, angular momentum is going to carry the loop through this area where actually zero force is acting on it. So in other words, because it's spinning, and it has mass, it's going to keep spinning. So that momentum will carry it through the area where zero force is acting on it from a magnetic field. Okay, at this point, importantly, we also need to change the direction of the current, or the loop is just going to pop back to that position where zero force is acting on it. Okay, and there's a small cuff on motor loops that will allow you to change direction. Okay, so next, well, that's it. Okay, guys, if you need any questions, hit me up on email, or probably the easiest way is to pop into my office hours, which I will have later today. Okay, have a great day, and I will see you soon.